last video today, 8.5, compare growth functions. All right. In our 8.4, we found two growth functions, or we found two running time efficiency functions. Yeah, because we use two algorithms. For this one, we want to compare which one is better. All right, so let's look at those two functions first. Yeah. The first one, our method one, we use the worst case. So we have this expression. Yeah. For the method two, we also use the worst case expression. We have another expression. Then we get their growth functions. The growth function, first we look at a dominant term. Then we remove the leading coefficient. So we get that growth function. Yeah. The second one, the growth function. So now we only need to compare these two functions. So which one corresponds to a more efficient algorithm? Yeah. The method is very simple. We take the ratio of these two functions. Then we look at the growth of the ratio. Remember, in our one of the previous videos, we talk about when we look at the efficiency of an algorithm, we should look at the data size very large. We should look at the case with large data size. Yeah. The larger the data size, the better we can see the efficiency. So that's what we have before. So we use this thinking here. Yeah. So let's take the ratio. Because we want to look at the trend when n is large, so we take the limit here. The limit, n goes to infinity. So that's we look at the trend, very large. Yeah. Then we simplify it. Yeah. So we look at this limit. Okay. Yeah. And here, because the denominator, the log at the denominator, we do not put any base, log base. So we assume we use some general log base, a. But this a must be greater than 1. It must be greater than 1. Then this log will give you a positive number. Yeah. So that's our assumption. Yeah. Under that assumption, we want to see if this limit is infinity or not. Infinity, so we know the top one grows faster than the bottom one. But the question is, how do we see it? How do you see this limit is infinity? Yeah. I like to use two methods to see it. The method one, variable substitution. Yeah. Because the denominator is a log, so we want to make the denominator as simple as possible. So we use a new variable u, let u be the denominator function. Yeah. Then, by the definition of logarithm, I hope you know the definition of logarithm. Okay? If u equals log base a of n, then we can write an equivalent form, n equals a to the uth power. Yeah. That's equivalent. Okay, these two expressions equivalent. Yeah. With that, now let's look at our original limit. We will get log, this time our variable u goes to infinity. Yeah. The numerator a to the u, denominator just u. Yeah. And the numerator is an exponential function, a greater than 1, exponential function, increasing exponential function. Denominator is a polynomial function. Yeah. How do you see that a to the u over u is infinity? How do you see that? Yeah. Here, some of you may know an exponential function always dominates any polynomial. We know that. Yeah. Exponential function, we know, increases very fast. So always dominates a polynomial function. Yeah. So if you know that basic fact, then you can get your answer. Yeah. But I believe many of you may not know why it is true, right? Why it is true. We want to prove it. Yeah. So here I can prove it. After we prove it here, next time you can use it. Yeah, without any hesitation. Yeah, just use it. Yeah. All right. In this slide, let's do it. Yeah. When we do it, I want to recall L'Hopital's rule. Yeah. I hope you know it. In your calculus, Calc 2 probably. Yeah. Some of you may not take Calc 2. So if you took Calc 2 before, so you have this background. Otherwise, you need to study a little bit. Okay? Try to find some online material to study. Yeah. But if you do not know it, let me just describe it. Then you just do it in this way. Yeah. All right, our method 2. We use L'Hopital's rule to calculate limits. Yeah. In this situation, L'Hopital's rule is a very powerful tool we can use to help us find the limit. Yeah. What's that? First, let me describe the L'Hopital's rule here. When we find limit of ratio of two functions, sometimes it is very difficult. We don't know how to do it. Then there is a possible way you can try based on the L'Hopital's rule. That is, you find the limit of the ratio of two derivatives. Because these two functions, we can calculate derivatives. Yeah. I hope you know how to calculate derivatives. If you can calculate the derivatives, you can use the L'Hopital's rule. Yeah. But when you use the L'Hopital's rule, you need to make sure the condition is satisfied. The ratio should be one of the indeterminate forms. There are several indeterminate forms. It should be one of the indeterminate forms. Yeah. One is infinity over infinity. That means the numerator goes to infinity when the variable goes to infinity. Or denominator also goes to infinity when the variable goes to infinity. In that case, you can use the L'Hopital's rule. Another, 0 over 0. Yeah. Here we're talking about the form 0 over 0. It's not really you take ratio 0 over 0 as a number. No, yeah, because in math, we do not allow that. right? In math, we do not allow denominator be 0. Yeah. But here, we use this as the form. That is, the limit of the numerator goes to 0. And the limit of the denominator also goes to 0. Yeah. So that's just a simple form we use to describe our situation. Yeah. If you verify all these requirements, satisfied, now we can do the, yeah. Now we can do the calculation. Yeah. All right. So let's take the limit. Yeah. All right. Now we can check it is infinity over infinity form. All right. Yeah. Then by the L'Hopital's law, we take derivative of the numerator, that is log n times a to the u. Yeah. Denominator 1, right? Now we can see when u goes to infinity, it is infinity. Yeah. Because a greater than 1. Yeah. All right. But here, yeah, one important thing I want to point out is we need to use continuous variables. Okay, continuous variables. Yeah. Yeah. All right. Because when we work on our limit, this is a discrete variable. So what is the discrete variable? This variable n only takes the value of 1, 2, 3, 4 integer values. That's discrete variable. When you have a function using discrete variables, you cannot take derivative. The derivative only has the correct definition only when the variable is continuous. Yeah. So in order to calculate, let's see, in order to calculate this ratio with discrete variables, we need to convert it to continuous variable. So here we use x, continuous variable. Okay? This time it's safe, we can take derivative. Right? Yeah. So after take derivative, I hope you know the formula, the derivative of log of x. Yeah. We use base a. Yeah. So we have that. Yeah. Then after simplification, we have this expression, and finally we get this infinity. Yeah. The last thing we can say, our conclude. Yeah. So all right. Yeah. So after we get that, for the continuous variable, we get its limit is infinity. Then we go back to look at the discrete variable. Yeah, because this variable only the special case of the continuous variable, right? So for continuous variable, the limit is infinity. Then we come back for the special case of the continuous variable. So for the discrete variable, we also have that. All right? So at the end, we make our conclusion. Our conclusion is the algorithm with the growth function n log n is faster than the one with growth function n squared. Okay? Yeah. So that's our final result. Yeah. All right. So we complete this last video of today. Yeah. All right.